All right. Yeah. So I'm excited to talk to you about um, some of my recent work with my collaborator Kieran Mastel on um, entangled constraint satisfaction problems. So the basic object we're studying here is something called a constraint system. So a constraint system consists of um, uh, it's a it's a it's a it's a system of equations essentially over some fixed alphabet. So it consists of a set of variables, here indicated by these dots, and a set of constraints on those variables. So essentially subsets of the variables, here circled, and constraints um, indicating what values those variables can be assigned to in conjunction. So here, for example, the colors being the alphabet, you have that the each set of variables is associated to some subset of the possible colors that can be assigned to this set of variables. Why CSPs are nice from a complexity theory perspective is that they sort of give a very versatile source of computational problems. The computational problem being that in the classical case, um, given given as a constraint system, can you find an assignment to all the variables, a global assignment to all the variables that locally satisfies each of the constraints on the subsets of the variables? This can be brought to the level of a language in the sense that you start with some fixed set of constraints and then you build up the possible constraint systems over larger and larger sets of variables that take those constraints and fill them in an arbitrary way with the variables. So let me give some examples if this seems very abstract. For example, 3SAT, very standard language. It's in fact a CSV language. So here the alphabet is the Boolean alphabet, Z2. The possible constraints are these single words in a 3CNF formula, just disjunctions of three different literals, which are either the variable or the negation of the variable. And then if you want all the constraints to be satisfied at the same time, you're looking for the satisfiability of the formula. There's just the conjunction of all of these terms. And then there is a satisfying assignment if this formula is not identically zero. So this is just the way to express this as a CSP problem. A very also similarly important, very different CSP is three coloring. Here the alphabet is ternary. There's three letters in the alphabet. There's a single possible constraint, which is the inequality constraint between two elements of Z3. The instances of graphs where you sort of see each edge as putting an inequality constraint between the two vertices, which are the variables. And this is the instance is satisfiable if the graph admits a three coloring. This is a special type of constraint system called a two constraint system because there's exactly two variables per constraint. This will show up a few times in the talk. So as I alluded to earlier, the sort of the complexity theoretic problem you can ask about a given CSP is you can ask what the complexity is of deciding if this constraints of deciding if a constraint system in the CSP, so an instance of the CSP, is satisfiable. This is a very well understood problem. So I'm denoting the sort of the classical standard version of the problem is CSP of gamma 1, 1, meaning that in the yes case, you want all of the constraints to be satisfied. And then in the no case, you want, and then the no case is anything that doesn't have all of the constraints satisfied. So there's no promise gap between the number of constraints satisfied in the yes case and in the no case. So yeah, this is very, 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 very well understood. It started with the work of Schaefer in the 70s, who showed that all Boolean constraint systems, constraint satisfaction problems, are either polynomial time or NP-complete. And there's been work over the last 2 decades that culminated in these two 2017 papers of Bulatov and Obzhuk, who show that the CSP problem is either contained in P or it's NP-complete. So this is sort of if P does not equal NP, this is a very different behavior to general computational problems, because in general you can have problems that sit in between P and NP, whereas here you have this dichotomy. And you can generalize these results a bit to gapped versions of problems, where here you have a promise that if if you're given a non-satisfiable instance, only a certain fraction of the instances of the constraints will be able to be satisfied at once by a given assignment, and this has the same complexity due to the PCP theorem. And you can also think about succinct versions of the problem, where you instead of being given the list of constraints as your instance, you're given a probabilistic Turing machine that can sample from the constraints, so that you could technically have exponentially many constraints, making this sort of a next complete problem if the sort of non-succinct version would then be complete to begin with. So now let's add quantum to it, and ask the question of, now that we have this constraint system, you have some constraints to satisfy, you have some variables that can be given values. You could turn this into a non-local game. And it turns out there's not one standard way of turning this into a non-local game. There's a few different ways. They're classically totally equivalent, but quantumly they do end up having different behaviors. So I'll go very, very quickly over the non-local games that correspond to each of these different presentations. So there's something called the constraint game, which, as the name suggests, consists of a referee and two players. And what the referee samples are pairs of constraints. The players each get a constraint, one of the constraints of the constraint system, and they should reply with assignments to that constraint. So satisfying assignments to just the variables in that constraint. And quantum players, of course, can share entanglement, but they can't communicate in order to come up with these assignments. And they win if on any of the overlapping variables between the two constraints, they have the same assignment. So there's the consistency check, essentially, making sure that the players are actually sort of building up parts of the same constraint system, of the same assignment to the constraint system. Of course, if they have quantum strategies, it's a quantum assignment, in which case they can sort of cheat in a non-classical way and get a higher number of constraints seemingly satisfied, higher fraction of constraints seemingly satisfied, even though you can't actually satisfy them at once. Similar sort of consistency checking variant is the constraint variable game. These are very close. The perfect strategies are, in fact, the same, but they do have slightly different behavior for imperfect strategies. And again, you have the same setup. You have a referee and two players who may share entanglement in the quantum setting. And instead of giving both of the players single constraints, you give one of the players a constraint, and the other player you give a single variable from the constraint. And what the players respond with, the first player, Alice, responds with an assignment to all of the variables in the constraint that should be satisfying. And the second player, Bob, responds with a single assignment to his variable that he received. And what the winning condition is again a consistency check. Alice's assignment, when restricted to the single variable that Bob received, should give exactly the same value as he gave. Now, the third version of the game is something called the two constraint system game, which is sort of special in the sense that you need the constraint system to be a two constraint system that you're playing the game with, meaning that every constraint is on only two variables. So here you have the same setup, but instead of okay, we're good. Instead of sampling a pair of constraints or a constraint and a variable, the referee samples a single constraint, and since there's two variables in the constraint, sends each of the variables, one to each player. And the players respond to assignments to those single variables. And now, instead of checking consistency, what happens is that the players win the game if their constraint was satisfying for their assignments put together was satisfying for the original constraint. So as I mentioned, these first two are very similar, but this third one, I mean, can have a different behavior. Now we can ask the same questions as we know the answer for classical CSPs about entangled CSPs, namely, what is their complexity? So the very general case is the complexity of non-local games is known, and the general non-local games, it's this celebrated MIP theory equals RE result of G, Natarajan, Vedic, Wright, and Ewan, showing that there's a polynomial time reduction from the halting problem to non-local games. But the non-local games are very general, right? They're polynomial length questions, polynomial length answers, and no real structure on the questions and answers. They're just general non-local games. So if we want to restrict to games, these specific CSP games that have a lot more structure, does the complexity stay undecidable, or does it immediately drop off? And for each of these models of the game, you can come up with similar entangled complexity classes doing the same decision problem as the classical case, except with now quantum players allowed. So what we show is that for many games, you do preserve the undecidability, you do preserve the hardness, and in fact, NP hardness often translates to undecidability for these entangled games. So we show a few cases. So if the original classical CSP was NP complete, and the alphabet is Boolean, so this is a 3-SAT, this captures 3-SAT, but not 3 coloring, for example, or the constraints are the 3-SAT constraint, or the constraints are the set of all 2 CSPs. So it's all the possible constraints. You can have a pair of variables over a fixed alphabet. Then in these 3 possible cases, we know that there is a polynomial time reduction from the halting problem to the corresponding succinct CSP problems with some gap in either the constraint variable or the constraint cases. So this tells us that essentially how we show this is that in these cases, we know that the classical reductions for NP completeness quantize to quantum reductions for RE-completeness. And we get a few corollaries of this result. And we also know that the 2CS game, in the cases that these are 2 CSPs, they also become RE hard. And because RE is a class where you don't really care about the time of the computational reductions, you also know that the non-succinct versions of these games are undecidable, even though there's not a polynomial time reduction specifically from the halting problem. So let's, before the end, I'd like to go through a little bit of the details of how the proof works of this result. And essentially, really the idea to keep in mind is that we're really quantizing the classical reductions that are already known to be possible. So there's these 2 major techniques that are based on earlier work of Mastel and Slofstra that we make use of. The first is the classical homomorphism technique. So really we're using the classical reductions that are known to say that we can take any arbitrary constraint system and then rewrite the constraints in terms of instances of the classical CSP using the classical reduction. So here, right, you start with sort of arbitrary constraints and you rewrite them as conjunctions of constraints for some specific CSP that you want to reduce to. So say, for example, 3-SAT. And the second reduction, the second sort of general reduction that we make use of is based on our improvement of an earlier reduction of Mastel and Slofstra that allows us to split apart these conjunctions of constraints into single constraints that get asked separately in different rounds of the game. So that sort of looks like this. We've sort of reduced from sort of general constraints of general form to constraints that have a specific form as conjunctions of constraints from a fixed CSP to now single constraints from the CSP. So we're really working at the level of the CSP language at this point. However, the second reduction, the subdivision reduction, there is an important caveat, which is that in order to guarantee, since for a single constraint, we know we need to have commutation between all the variables of the constraint. And in order to guarantee an approximate version of that in this subdivided constraint system, we really need to make sure that every pair of variables appears in at least one constraint. And how that's sort of a naive way to do that is to add so-called empty constraints that don't actually constrain the variables at all, They just make sure that the players can measure their assignments to the variables simultaneously. But that's not nice, because empty constraints don't belong to the CSPs we're interested in. So we want to get rid of them somehow. So what we do is we construct something called a commutativity gadget, which is a specific small constraint system that allows this empty constraint to be simulated by forcing the variables to commute while not putting any additional constraints on them. So for a large class of games, constraint satisfaction problem that we call the non-two variable falsifiable problems, we can build like generic commutativity gadgets. So we say a constraint system is a constraint satisfaction problem is whether a constraint or a constraint satisfaction problem is two variable falsifiable if essentially if for any pair, if it's non-two variable falsifiable, which is really the condition we're using, if there exists a pair of variables that you can assign to any value and then extend that assignment to a satisfying assignment to the whole constraint. So essentially what you do is you use this constraint where you have these variables you can extend and add dummy variables to the extension, so that no matter what pair of variables you have in these sort of distinguished positions, there's always an extension that makes it satisfied. So there's no constraints on the variables in these distinguished positions, but they are part of the same constraint, so they have to be measured at the same time, and therefore they should commute. And so just an example of this, again, in the concrete case of 3-SAT, we want to say x and y to commute. We put them in the constraint x or y or z, where z is a variable that appears nowhere else. So by setting z equals 1, this is a constraint that's always satisfied, irrespective of the value of x and y. So this gives like a very general class of very easy to construct commutativity gadgets. However, there are lots and lots of CSPs that don't satisfy this property. A sort of glaring example is 3-coloring. Any 2 CSP doesn't satisfy the property because you really can't any 2 CSP rather that is not that doesn't already contain the empty constraint doesn't satisfy this property because there's only 2 variables. You can't extend it in any way. So these are the two variable falsifiable CSPs, and for some of them we are also able to construct commutativity gadgets. And this case really is why we were not able to construct to get the hardness reduction for all CSPs, is because these commutativity gadgets can be quite esoteric in nature and really need to be constructed on a case-by-case basis. So I'll show you a couple of the constructions that we have. So in the case of 3-coloring, where as I said earlier, we can see instances as graphs, we can use a commutativity gadget originally proposed by G. And what you do is if you want a pair of variables to commute, you put this sort of weird triangular prism graph between them. Remember, each edge is a 3-coloring constraint. And it turns out, due to the algebraic properties of the algebra generated by this graph, we know that we don't have any constraints on the values that these red variables can take, but we do constrain them to be commuting. Another construction that we make use of in order to fill in the rest of the Boolean CSPs is this construction of the 1 in 3-SAT commutativity gadget. So 1 in 3-SAT is the Boolean CSP on 3 variables, where the 3 variables are constrained to have only one of them be 1, and the rest of them have to be 0. So you can see this sort of like a triangle, like a triangular edge in a hypergraph. And again, due to G, there's an interesting gadget where if you want these 2 vertices to commute, which sort of are on corners of a hypergraph, you can build this sort of inverted triangle construction to make sure that, and this again works by the algebraic properties of this this constraint system. you do end up with the same condition that these two red variables can take any value, but they have to have commuting measurements. And it turns out that this generalizes a lot. Every two-variable falsifiable CSP can be used to simulate a single 1 and 3 set constraint, and then these three of these 1 and 3 set constraints can be stitched together to make a commutativity gadget. So this single constraint, the single commutativity gadget generalizes to a commutativity gadget for every every two-variable falsifiable Boolean CSP, meaning that that we've actually, with the two cases, the non-two-variable falsifiable CSPs from the previous slide and these two-variable falsifiable CSPs from the current slide, we've covered all of the possible Boolean cases. So let me sketch the whole proof very quickly to finish. So it's based on it starts from a refinement of MMP star equals RE due to Dongfu, Natarajan, Chin, Xu, and Yao. And here, the special thing that they do is they still have polynomial length questions. So the question, asking the questions is a succinctly presented thing, but the answers are constant length. So there's constant size answers. So the first thing to do is to turn to use an oracularization transformation to turn this into a constraint system game of some kind. And now the classical homomorphism can be used to replace these unstructured constraints by structured constraints. And then subdivision can be used to split them into constraints from the particular CSP we're interested in reducing to, along with these empty constraints to guarantee commutation. Then to finish, we convert via homomorphism of the corresponding algebras to the constraint variable version of the game, and then we can apply the commutativity gadgets in order to remove any empty constraints. So because of this final step, this reduction really requires the existence of a commutativity gadget for the particular CSP we want to reduce to in order to get the hardness reduction that we'd like. So to finish, what we show is that many NP-complete CSPs do end up becoming RE-complete when you play them as a non-local game. Due to some earlier work, it's known that there's a gap below which it becomes easy to approximate 3-set, and above, and now because of this work, we know that there's a gap above which it becomes undecidable. So there's this very strange sort of a hardness of approximation regime where up to a certain gap size, it's actually in polynomial time to find the value of 3-set, and above a certain gap size, it's undecidable. So in between there, I think it's an interesting place to ask what happens. Is there a sharp jump from polynomial time to undecidable, or does it go through a lot of complexity classes along the way? And then so I'll finish with a few open questions, a little bit of recent work in this direction. An open question is, what about the rest of the NP-hard CSPs? Do they become undecidable with entanglement, or are there some undecidable, some NP-hard CSPs that become decidable once played with entanglement? And the other sort of the converse of that question is, are there classically easy CSPs that become hard once you play them with entanglement? A possible example of this is the linear systems, which are easy classically, and we know in the zero gap case they are undecidable with entanglement, but in the gap case that's unknown, and it's a big open question. And there's some new developments in this direction based on some of my recent work with Josef van der Braun, Matthias Benoit, and Peter Zeeman. And what we show is that there actually exist CSPs that do not admit commutativity gadgets. And sort of the strange thing about that is that now we know that for these, if we want to show that they're undecidable, we cannot just quantize the classical reductions. We have to do some natively quantum reductions that might have a completely different structure to what we might expect CSP reductions to look like. Yeah, anyway, thanks for listening. I hope you enjoyed the talk. Questions?
Hi, sorry. So one question. I didn't quite understand the setup now with entanglement. So you're allowing Alice and Bob to have access to a quantum computer, but what they should output is still a classical, like a bit.
Yes,
Am I
yes. So
correct?
it's
Okay.
this it's a setting of non-local games where the input and output are classical, but the special thing that Alice and Bob can do is that they can share an entangled state, right? So they have access to a larger set of correlations than anything that's possible classically, and that can do a lot for the their ability to satisfy constraints.
And as a second question, do you know of any results that, like a dichotomy, but for the gap at the end that you were mentioning, that you might have like P and then it becomes undecidable? Can you sometimes prove that it's just 2 cases or 3 cases or something?
I don't think there's any results that show that explicitly. I mean, the closest hardness to like a hardness of approximation type result is this recent result of Thaler and Vidic for um, um, linear constraint systems, where they show that like you can make the gap between the yes case and the no case for linear constraint systems arbitrarily large, and retain undecidability, but you can't take it all the way to 1. It's using again a quantization of a classical reduction due to Hastad. And another direction is recent work of Musavi and Spirig that's sort of trying to find the right quantum version of the unique games conjecture, because classically a lot of hardness of approximation results rely on the unique games conjecture. So up to this conjecture, it's there are some quantum problems that are known to have this sort of sharp jump from easy to undecidable.
Yeah, thanks for nice talk. So this question is naive question, not exactly related to your work. So you say binary constraint system or constraint system in general can be mapped into a non-local game. So now, but here you discuss the mainly bipartite non-local game. But we know that there are multipartite non-local game we can define. So is there a constraint system, something variation to multipartite?
Yes, absolutely, absolutely. I mean, I don't think there's been much work on this, but one really sort of perhaps striking example of this is this 2 constraint system case.
I see.
If you increase your arity of your constraint system, then you get one way to play it is you can increase the number of players.
Yes.
And ask each player one of the variables. And that would be a way to extend it. But the difficulty is here we're really relying on like a synchronicity. We're really relying on a synchronicity condition to simplify the algebra and make it more tractable. And that allows you sort of to see Alice's and Bob's measurements is essentially in the same algebra. But if you increase it to a larger number of players, because of monogamy of entanglement, you cannot do consistency checks, right? You cannot always pass if you do consistency checks, and therefore you can't guarantee that like Alice's way of measuring a specific variable and Bob's or Charlie's or Dave's or whatever ways of measuring the same variable are the same. So they could be wildly different. So the behavior is sort of not. I don't think it will really look anymore like a quantum assignment to a constraint system, but it'll look like something different.